Hello, in this podcast we're going to learn about force and potential energy. First we're going to explore potential energy, then we're going to move on and look at conservative and non-conservative forces, and finally we're going to look at the role conservative forces play in potential energy and the role that non-conservative forces play in kinetic energy. Let's get started. Potential energy is the energy stored in a particle's or object's position in space or physical configuration. And potential energy can perform work on particles and objects. Here's our equation relating the change in potential energy and the amount of work performed, and it tells us that the work performed is equal to negative the change in potential energy. And of course that flips the order of our initial and final potential energies in this subtraction. As we discussed earlier, there's two types of potential energies. Let's take a closer look at each one. First, we'll look at gravitational potential energy, and this is the energy stored in a particle's position in space. In other words, the particle, no matter where it is in the universe, is going to be in some gravitational field, and it has the potential to move towards that center of the gravitational field. And that means there's energy stored in that space or distance above the center of the gravitational field. And our equation for that is the potential energy is equal to the mass times the strength of the gravitational field times y or h. We sometimes use them interchangeably. Y and h are simply the distance above an arbitrary reference point. We typically set that reference point at the lowest point the object will get in its motion. And in this example, the box is going to be stopped by the floor. So we would set the floor as our zero reference point, although that's completely arbitrary. In this case, when we're talking about gravitational potential energy, the work is being performed by gravity or the gravitational field. And our equation for that is that the work performed is equal to negative the change in the potential energy. And again, you can see that flips the order of our initial and final positions. So if you're like me, when I first saw this, I right away said, well, why is work equal to negative the change in potential energy? Let's look at that. First, we need to remember the flow of work. If work is positive, that means the energy is flowing into the object feeling the force. Or in this example, if work is positive, that means that energy is flowing from the gravitational field into the falling box. If work is negative, then energy is flowing into the object exerting the force. In this example, that means that energy would be flowing into the gravitational field, and of course that means that it would be flowing out of the falling block. So looking at this example, from Earth's gravitational field perspective, as the block's position decreases and gets closer to the floor, the energy stored in the gravitational field, the potential energy, is decreasing. And from the block's perspective, as it's falling towards the floor, its speed's going to increase, so its kinetic energy is increasing, and that means its mechanical energy is increasing. Hence, work is positive because energy is flowing into the object feeling the force of gravity. Finally, if the gravitational field is part of the system, then the force is internal, the energy flow within the system is internal, work is internal, and that means there is no external work performed. Typically, when we solve these problems, we do make the gravitational field part of the system. That way we can have potential energy in the system. So please remember that gravitational potential energy belongs to the gravitational field. If the gravitational field is part of the system, then your system can have gravitational potential energy. If you do not make the gravitational field part of the system, then that potential energy lies outside the system and your system will not have any gravitational potential energy. Rather, that'll be recognized as energy transferring into or out of the system via the work transfer mechanism. Let's move on and look at the other potential energy, elastic potential energy. And that's the energy stored in a particle's configuration, more commonly known as being stored in its temporary stretch or compression. Most often we're looking at springs when we're talking about this, but it could also be rubber bands, bungee cords, rubber balls, things that have tennis balls, things that have the ability to temporarily compress or stretch and then return to their normal shape. This is our equation for calculating the elastic potential energy. It's 1/2 times K times X squared, where K is the spring constant, keeping in mind that stiffer springs will have higher spring constants, and X is the distance of stretch or compression beyond the normal shape. We often call this normal shape the equilibrium position. The work performed by the spring is equal to negative the change in the elastic potential energy. Again, we ask ourselves, why negative delta U sub S? Thinking back again to our workflows, positive work means that energy is flowing into the object feeling the force. In this case, energy would be flowing into the block. Negative work means that energy would be flowing into the object exerting the force. In this example, that means that energy would be flowing into the spring, and of course it would be coming out of the block. Let's look at this from the spring's perspective. When it's launched, its position X is decreasing because it's getting closer to the equilibrium position of 0, and that means that the potential energy stored in the spring's compression is also decreasing. Looking now from the object's perspective, it's going to start moving and speeding up, so its kinetic energy is increasing, which means its total mechanical energy also increases. Hence, work is positive because the energy is flowing into the block, which is feeling the force. Finally, if the spring's part of the system, then the force is internal, energy flows within the system. We say that work is internal, and that means there is no external work being done. So we typically will make the spring part of the system along with the block. However, if you make the spring part of the surroundings, then we have to keep in mind the block can have no potential elastic energy, because that goes with the spring. So if you want your system to have elastic potential energy when you're solving this problem, you need to make the spring part of it. If the spring's not part of the system, then the energy it imparts to the block will flow through an external force and be external work. Let's work through a simple problem on calculating potential energy. Here we've got a pop gun. It has a spring that's compressed from its equilibrium position, and it has the ability to launch this ball. So find the potential energy of the 50 kilogram bullet when the compression is 1/10 of a meter and the spring constant is 150 newtons per meter. Here's our potential energy equation. Notice we have both gravitational potential energy and elastic potential energy because we have a change in the position of the spring, but we also have a change in vertical position, also known as height. So we go ahead and plug in our numbers. This first part is calculating the gravitational potential energy. Notice the negative sign in here means that energy is flowing out of the ball when we compress it from this 0 point. And then here is our elastic potential energy. Notice regardless of whether the spring is compressed or stretched, the elastic potential energy is going to be positive, because energy is being stored in the compression or the stretch. Whereas with gravitational potential, energy is lost. Energy flows out of that potential mechanism if the ball moves closer to the center of the gravitational field. We go ahead and plug in our numbers, and we find that this ball has 0.7 joules of potential energy. Now we're going to move on from potential energy and talk about two important forces or types of forces, conservative and non-conservative forces. With a conservative force, the work performed by the force is independent of the object's path. The force performs no work on an object that starts and finishes in the same position. The two most common examples of conservative forces are gravitational fields and springs. Non-conservative forces are different. If an object starts and finishes at the same position, work is being performed and energy is being dissipated along the path. So that's different than conservative forces, where if an object starts and ends at the same spot, there is no change in energy and no work was performed. But regardless of the path taken, with non-conservative forces, energy is dissipated along the entire path, so that even if an object winds up back at its starting point, work was done to get it there. Most common examples of non-conservative forces are friction and drag. So let's take a look here. We've got 4 different inclines. The balls all start at the same height and they'll all end at the same height. Without friction, in other words, with only the conservative force of gravity acting on it, the same amount of work is performed in all 4 instances as the ball rolls down to the bottom, and the ball will be at the same speed at the bottom of the ramp in all 4 cases. If we take the ball when it reaches the bottom of the ramp and we push it back up to the top, we'll find that the amount of work performed on the ball to move it back up to the top is equal in magnitude to the amount of work the gravitational field performed on the ball to move it to the bottom of the ramp. These workflows are in opposite directions, so when we return the ball back to its original position, the net work performed on the ball is 0. And that's what we mean by this definition up here. Force, the conservative force, performs no work on an object that starts and finishes in the same position. However, if we have friction, a non-conservative force, things are different. The amount of work performed in each of these cases is different. And if we measured the paths of each of these shapes, the incline that had the longest path would be performing the most, friction would be performing the most work on it. So I haven't measured these exactly, but my guess is that C has the longest path. Speeds at the bottom are going to be different, not the same. The path that is the longest is going to have friction causing the greatest impact, will be the slowest at the bottom of the ramp. I suspect that in these 4 cases, the ball at the bottom of ramp C is going to be the slowest speed. Finally, if we take the ball from the bottom of the ramp and have it go back up to the top of the ramp, we're going to find that there was work performed to have the ball go down and back up because we are dissipating energy because of the friction force both going down and back up the path. Let's move on and explore the relationship between conservative forces and potential energy. If we have a conservative force acting on a system that starts at rest and ends at rest, then we know that the work is equal to negative the change in potential energy, or U sub I minus U sub F. We can substitute this integral for work, and that leaves us with this expression. Starting from there, we can come up with a potential energy function. We go ahead and rearrange this equation for the final potential energy in the x dimension. That's equal to negative the work integral plus the initial potential energy. If the initial potential energy is 0, then our equation for the final potential energy in the x dimension is equal to negative the integral f of x, the force in the x direction, dx, evaluated from x sub I to x sub f. We can look at a conservative force function. For an infinitesimal displacement, we know that du is equal to negative f sub x dx, where du is the infinitesimal change in potential energy caused by a force acting parallel to an infinitesimal displacement. And we can rearrange that and come up with the force parallel to the displacement is equal to negative the derivative of the potential function with respect to the displacement x. Let's take a look at how we use this. And we're going to calculate force from a potential energy function. So we have a potential energy function for a 2-dimensional force, and it is U equals 3x cubed y minus 7x. So we want to find the force that acts at the point xy. Because U is a function of both dimensions, that's why they call it a 2-dimensional force. We have to look at each dimension separately. The force in the x dimension is going to be equal to negative du dx. So we go ahead and differentiate this expression with respect to x, and we come up with 7 minus 9x squared times y, and then we have to evaluate the y component of the force. So we're taking the derivative of the potential function with respect to y, and of course the force is equal to negative that. We're left with the y component force being negative 3x cubed. Therefore, we can write the two-dimensional force in our unit vector notation, 7 minus 9x squared y times I minus 3x cubed times j. Now, if we were given a specific value for x and y, we could plug those in, and that would give us our force in unit vector notation. Let's move on to non-conservative forces and kinetic energy. There are three ways to change kinetic energy. The first way is internal conservative forces, and in this instance, all energy flows from potential to kinetic or vice versa. Mechanical energy is conserved, so we know that the change in kinetic energy caused by internal conservative forces is equal to the energy transferred out of the potential mechanism. The second way to change kinetic energy is internal non-conservative forces. Here, energy flows from potential energy to kinetic energy and dissipated energy. So the difference here when the force is non-conservative is energy is flowing from potential, but not all of it's going into kinetic, like up here with conservative forces. Some of it is being dissipated. So the mechanical energy is reduced by this dissipated amount, and so the change in kinetic energy caused by internal non-conservative forces is equal to the energy flowing out of the potential mechanism minus the energy that's dissipated. The third and final way to change kinetic energy is with external forces. If the force and displacement are in the same direction, then energy flows into kinetic. If the force and the displacement are in opposite directions, then the energy flows out of the kinetic mechanism. The change in kinetic energy caused by external forces is equal to the work. That leaves us with an overall equation for the change in kinetic energy. It's equal to the change caused by internal conservative forces plus the change caused by internal non-conservative forces plus the change caused by any external force, either conservative or non-conservative. Armed with this overall equation, let's look and see how we can determine the amount of energy dissipated. I'm going to start with that overall equation we developed at the end of the last screen. We can restate this in different terms. So we know that the change in kinetic energy caused by both types of internal forces is equal to the energy that flows out of the potential mechanism minus the energy that's dissipated by the internal non-conservative force. The change in kinetic energy as a result of external forces is going to be equal to the work performed by conservative external forces less the work performed by external non-conservative forces. We can rearrange this and come up with the total energy dissipated is equal to the energy dissipated by the internal non-conservative forces plus the work performed by the external non-conservative forces. And that in turn is equal to the work performed by the external conservative forces minus the change in kinetic energy minus the change in potential energy. When non-conservative forces are external, in other words, we have no internal conservative forces, this relationship exists, that the net work creates the change in kinetic energy. All this is telling us is that the work performed by external conservative forces less the work caused by external non-conservative forces is going to create the change in kinetic energy. Let's take a look at calculating dissipated energy. A parachutist of mass 50 kilograms jumps out of an airplane at a height of 1,000 meters and lands on the ground with a speed of 5 meters per second. How much energy was lost to drag during this jump? I'm going to treat the gravity force as an internal force and the drag force as an external force. And the reason I'm doing that is that allows me to have no E dissipated internal, and it also allows me to deal with the gravity force through the potential energy equation. So I can take my base equation and rearrange it to the total dissipated energy is going to be the work performed by the drag force, and that's going to be equal to the negative change in kinetic energy minus the change in potential energy. So what we're saying is that the dissipated energy is going to be the energy flowing out of the kinetic mechanism plus the energy flowing out of the gravitational potential mechanism. Here's our specific equation to calculate that. And when we go ahead and plug in our numbers for mass, final and initial velocity, gravitational field strength, and height, we find that the energy dissipated by the drag force was 489,000 joules. Well, this ends our podcast on forces and potential energy. I hope you found this helpful, and have a good day.